Hello, everyone. I would like to start by thanking the organizers for giving me the opportunity to give a talk. This is the very first time I give a pre-recorded talk for a conference. This is very interesting, and I can only think of as being very useful. Let me start by saying that my talk will be consisting in two parts. The first part being some background and context for the actual result that I will be presenting. And I would like to start by saying that everything that I will talk about today is joint work with François Tilmany from Louvain. So the title of the talk is Arithmetic Groups and the Lehmer Conjecture. And all of the notions will be introduced. I hope that it is sufficiently self-contained and that everyone will be able to get something interesting out of this. So let me start with the first part. So I will talk about lattices and more specifically uniformly discrete lattices, which are the main object of study here. Now, very likely because the conference audience consists mainly of people interested in geometry and topology. Many people are already familiar with this, but I will nonetheless start with some basics just to ease up. So we always work in locally compact groups, and here's the general setup. We have a locally compact group G, and gamma is a discrete subgroup inside of G. So gamma is called a lattice in G if the quotient G mod gamma has finite volume with respect to a left invariant Haar measure. The very basic example, the simplest example would be to take the real numbers for G, the integers for gamma, and then the quotient is just a torus equipped with the Lebesgue measure, which is the Haar measure. And this quotient has finite Lebesgue measure. And so this is not a lattice. Here's the non-example. If you take G equals R and gamma to be alpha times Z, where alpha is an irrational number, however, then this gamma will be dense in G. And so the embedding is actually quite important in this setup. When G is a billion and gamma is a lattice, then the quotient, as we observe here, is compact. It is always the case when G is a billion. In this case, we say that gamma is a uniform lattice. And if it is not, or that gamma is co-compact in G, if it is not compact, we say non-co-compact or non-uniform. So there are some constraints to containing lattices. So we cannot just take any locally compact group and hope to have a lattice. There are some consequences for this. The first being that if G contains a lattice, then it must be unimodular, meaning that the left invariance of Haar measure also implies right invariance, so that the modular function is actually identically equal to 1. Here's an example of a group which has no lattices. So if you take the group of 2 by 2 matrices with A inverse on the diagonal and B in the upper right corner, this is a symmetric product of the multiplicative group of the reals with acting on the reals, and this symmetric product is not unimodular, and it contains no lattices. So to see that it's not unimodular, you can simply compute the Haar measure and observe that this is not possible to have the modular function equal to 1. So how do we distinguish between compact and non-co-compact lattices? There are multiple ways to look at this. The most somewhat general criterion is the Godement compactness criterion. And here is the setup. Take a closed subgroup of GL and R. This works in, there are extensions of this criterion to more complicated settings, but we will always work with the Lie groups or matrix groups. So if G is a closed subgroup of GL and R, and A is a subring, we can define G intersecting with SL and A. And we said that G is defined over Q if G is defined as the vanishing set of polynomials with coefficients in Q. The theorem says that if G is defined over Q, then the quotient of G mod GZ is compact if and only if GZ has no non-trivial unipotent elements. Now, this suggests that the quotient G mod GZ is going to be our prototype for the homogeneous space G mod gamma, where gamma is a lattice. So just to illustrate this, if G mod GZ were to not be compact, what can we do? Then in a non-compact quotient, there would exist an element in GZ and a sequence of elements such that conjugation would actually converge to the identity. But looking at the characteristic polynomials, we would also have that the characteristic polynomials converge to the characteristic polynomial of the identity. But since the characteristic polynomial is invariant under conjugation, and gamma is in this case in SL and Z with integral entries, then it follows that it must be exactly the same characteristic polynomial of the identity, which implies that it is indeed unipotent. So here are some examples of lattices. I will try to go through 2 examples, actually 3, but 2 in more details than the last one. So let me start with the following. Let's say we take SL2, we take SL2R, and we take SL2Z. So in the previous notations, we have G, and gamma is indeed here GZ, G sub Z. Now, SL2Z is a non-uniform lattice because precisely it has non-trivial unipotence, as is easily observed with the 1x01 matrices. So the compactness criterion tells us it's non-uniform. To see that it is a lattice, there are multiple ways to look at this, but in practice, one way to do it is to look at the quotient of G by SO2, in which case you could identify this with the upper half plane, and then gamma acts on the upper half plane. And then we can show that there is a fundamental domain for this, which has finite volume. Everything can be computed explicitly using the Haar measure and the Iwasawa decomposition. Here's a somewhat more complex example, but still in the same line. So if I take Q adjoint square root 2, this is a number field, and I take Z square root 2 to be the ring of integers. This is a quadratic extension of Q. Then I take sigma to be the non-trivial automorphism of K. Then this embedding will give me the embedding of the ring of integers into 2 copies of C by mapping X to X and X the conjugate will then induce an embedding of SL2O into the product of SL2R with SL2R. And in this case, if you take a matrix and you apply the Galois conjugate, the Galois automorphism, this is by definition applying the automorphism to each of the entries of the matrix. So this embedding gives me the image of SL2 Z square root 2 inside this product, and will give me an arithmetic lattice in this way. This arithmetic lattice will be non-uniform. So if we look at this in a little bit more details, I will try to give a few details about this. This is the same notation as before. Now I take the vector space V to be R4. Now, what is delta of K? Delta of K is going to be a Q form of R2. The definition of this is precisely that by extension of scalars tensoring with R, we obtain R2. So, of course, if I define VQ to be delta of K squared, then this becomes a Q form of R4. Now, we work with groups of matrices. So we want to look at the endomorphism space of V. Now, the endomorphism space of V, I'm looking for a Q form, meaning that when I tensor with R, I will also obtain the endomorphism of V. So one way to do this is to define precisely that form to be all the matrices which preserve this subspace. of the subspace VQ. So inside K4, I'm looking for specifically vectors of the type U sigma, and I take all the endomorphisms that stabilize this subspace. And this subspace is then a Q form, in that when you tensor, you obtain indeed the NV, and we can write it down somewhat explicitly. So if G is an element of this Q form, so an element which stabilizes the vector space VQ, okay, then the condition of that it stabilizes the subspace can be written as G to be of the form A, B, B sigma, A sigma, where A and B are now two matrices in 2x2 matrices with entries in K. So that, as we can see, the endomorphism G is written explicitly with matrices 2x2 together with this Galois automorphism. So using this, it follows that when we take the image of SL2 of the ring of integers in this way, then we take the elements which stabilize the image of O square. And the image of O square is actually going to become VQ when tensoring with Q. So in a way, this is a Z form of VQ. Now, going all the way, the image X sigma, where X is now in SL2O, right, which is the image of SL2 under delta, is then going to be an arithmetic subgroup of SL2R cross SL2R. Now, what is an arithmetic subgroup? This is just the construction that we have worked here with, where we construct something from the integers. Now, if we were to try and extend this, it's possible in multiple ways. We can replace, for instance, SL2 with any algebraic Q group. So, in SLN. And we want to observe something, which is that gamma here is irreducible. So it's not like we take SL2R, we take a lattice, and then we take SL2R and take a lattice, and we just take the direct product of those. This lattice sits inside SL2R cross SL2R in a non-trivial way. It projects trivially on each factor. This process has a name, which is often called restrictions of scalars. It allows to work originally with number fields. In this case, the number field was Q square root 2, and going back to Q to work with an algebraic group defined over Q. So in general, the context is that we take a Lie group that comes from an algebraic construction. In this case, we take an algebraic group G defined over a number field K. For instance, we can take SLN, which is defined over Z, and we can take the K tensor R points of this algebraic group. This gives us a Lie group. And we take gamma inside of G to be a lattice. So this is usually how the type of groups we like to work with. Of course, they're not the only type of Lie groups. They're not all algebraic. But in terms of what can be said about them, it not only does it facilitate certain things, the Lie groups coming from algebraic groups tend to have very particular features. So to that end, let me state the very famous theorem of reduction theory from Boyle and Harish-Chandra from '62, which is that if we take a semi-simple Q group of SLN, then the Z points of G, which are now defined simply as taking the Q points in the embedding and intersecting with SLNZ, that G of Z is then a lattice in G of R. So this is a famous theorem of Boyle and Harish-Chandra that tells us that whenever we are going to carry out this a construction of this kind, we are going to obtain finite volume homogeneous space. So here is going to be our general definition of arithmetic lattice. So if we have a Q group, G, and we take G of Q intersect with SL and Z, so G of Z, if we have gamma inside some Lie group, and gamma and GZ are commensurable for some embedding inside SLN, of G inside SLN, then gamma will be called arithmetic. So commensurable means that it's finite index in the intersection. Sorry, that the intersection is finite index in the original groups. So they are, to a certain extent, of similar sizes. But more generally, we can take gamma prime and phi of gamma to be commensurable, where phi is a surjective morphism with compact kernel, and then gamma prime will then also be called arithmetic. These are very general definitions. They will not matter too much in this context, in the sense that I will work with very concrete examples. But these are what the definitions are. So let me go now to my second example, which is the more important one in the context of unitary groups. So similarly to before, I will work with some number fields. So let me put A to be square root 2, K to be Q square root 2, and then L to be Q fourth root of 2. So I have the extension L over K. So observe that K is totally real, right? And that actually it is the fixed field of L where for the automorphism of order 2. Now, the group that I'm going to use this time is going to be the special unitary group of a Hermitian form. So if I take the standard Hermitian form over L, so is going to be x1, y1 bar, x2, y2 bar, where the bar denotes the automorphism of L of order 2. Then this actually defines an algebraic group. This algebraic group is defined over K, and its K points are going to be equal, isomorphic to the matrices 2 by 2 with entries in L that stabilize the Hermitian form. They have determinant 1 in this case. Now, if we go back to K, we have two embeddings, or the identity embedding, and then we have the other automorphism that sends square root 2 to negative square root 2. These two embeddings are going to give me two completions for L and K. The completion with respect to identity embedding is, of course, the real numbers. And for the other one will be the complex numbers, precisely because the square root is of a negative number. So with that in mind, it will give me the ability to compute precisely the points of the algebraic group. In this case, it just gives me an isomorphism for each of the places, for each of the valuations. So for the identity embedding, I get SL2R. And for the non-identity embedding, I will get SU2R, which is going to be SU2. And this SU2 is going to be compact. In the first case, the completion contains L, so it must be SL2R. And the second case, the Galois automorphism sense is going to make the form positive definite in the completion, which implies that the group is going to be the usual unitary group. So that's all good. Boyer-Chandra theorem implies then that the way that I have constructed this subgroup inside this direct product is an arithmetic lattice via the restriction of scalar. Just a remark here, the restriction of scalar works from the fact that originally I had a group that was over K, and K was a degree 2 extension of Q. The Boyer-Chandra theorem works with Q groups, and so I can construct a Q group from a K group and apply Boyer-Chandra theorem, which is exactly what the statement here says. It gives me the embedding to be inside this direct product, each factor corresponding to one place, to one embedding. Now, this G of OK that I have defined inside this direct product through the restriction of scalars shows me that when I project onto the SL2R factor, this projection will have compact kernel. So the kernel is going to be SU2. And this tells me, in fact, that the image inside SL2R is going to be a co-compact arithmetic lattice. And so this is just one example, but more generally, we can vary K, L, and H appropriately to obtain all possible arithmetic, co-compact arithmetic subgroups of SL2R. Now, in order to obtain all arithmetic co-compact subgroups of SL2R, it is necessary to vary K, L, and H in an appropriate way. So we can have different Hermitian forms. We can have different number fields. And if we try to go in higher dimensions, the remark is that it becomes also necessary to consider not just field extensions, but actually central simple algebras. Now, a question that comes naturally, because we just constructed all of this, is can we always do that? Can we always construct lattices? Now, it is not always true. All lattices are not arithmetic. However, Margulis proved somewhat of a converse. So the statement of Margulis' celebrated arithmeticity theorem is that if you take a semi-simple real group of real rank greater than or equal to 2, if gamma inside the R points is an irreducible lattice, then gamma must be arithmetic. So the only restriction is the real rank. This, of course, will exclude SL2R, where SL2R does contain non-arithmetic lattices. But if you go SL3R and above, you can take also symplectic, and it will not be possible to have a lattice which is not arithmetic. So let me continue with uniformly discrete lattices. What is this? If I look at a connected linear semi-simple Lie group with their compact factors, these assumptions come from the fact that we want those Lie groups to come mostly modulo connected components from an algebraic group. Then Kazan and Margulis proved in 1968 in their respective second paper that there was an identity neighborhood such that for any lattice inside the Lie group, there is a conjugate which intersects this neighborhood trivially. So the Lie groups and the lattices in there have some fairly important constraints. Now, the consequence of this is that if in particular gamma is non-uniform, then gamma must contain a unipotent element. The consequence of the arithmeticity theorem, which improves on the statement of Kazan and Margulis, is that if you take, of course, in the same assumptions of the Margulis arithmeticity theorem, if you take a connected semi-simple real group of rank greater than 2, in the R points, you can find an identity neighborhood which has the following property. For any irreducible non-uniform lattice, then the intersection only contains unipotent elements. So this is a fairly strong restriction. It means that inside the lattice, the only way to approximate the identity is by unipotent elements in a uniform way. What about uniform lattices, co-compact lattices? Margulis, in his book in 1991, wrote the following conjecture. If we have the same assumptions, connected semi-simple real algebraic group, we can find an identity neighborhood of the R points, such as for any irreducible co-compact arithmetic lattice, the intersection with this neighborhood only consists of torsion elements. The arithmetic here is, I will come back in 1 second, why I added arithmetic. Essentially, what this conjecture states is that torsion-free arithmetic co-compact lattices are uniformly discrete. If you are torsion-free, then there is an identity neighborhood that will be avoided by all co-compact arithmetic lattices at once. Technically speaking, this conjecture has been modified a little bit because Margulis' original conjecture has real rank greater than or equal to 2. But in fact, imposing arithmetic instead of real rank greater than or equal to 2 allows us to include the case of rank 1.